Hello, my name is Joanna Kim, and this is my report on Lab 2 Projectile Motion. The purpose of this lab is to observe the projectile motion of an object both computationally using GlowScript and experimentally using Tracker, and to compare the object's motion when influenced solely by gravity versus when affected by both gravity and drag. In this case, the system is the moving object, which is the red stress ball, and the surroundings is everything else such as the air around it, gravity, and air resistance. The physics principles used in this lab is Newton's second law and the drag force formula. Newton's second law states that the net force acting on an object is equal to the change in time of its momentum, as shown in the equation F net equals dp over dt. After rearranging this equation, we can derive the momentum update formula, the velocity update formula, and position update formula. We will be applying the momentum principle to update the velocity and position of the object at each time step. The drag force equation will also be used in this lab to calculate the force on the object from air resistance. In this equation, B is a proportionality constant that is determined based on the experiment data. In the computational model that accounted for both gravity and drag, I set the drag proportionality constant to 0, which left my model with just the force of gravity acting on the object. V is the velocity, and V hat is the unit vector indicating direction. These equations and concepts will later be used when making our computational model. These are the steps I took when experimenting this lab. First, I recorded the motion of the object moving in a projectile motion. Then I analyzed the video of the observed motion using Tracker to get the object's positions and corresponding times. After that, I used the physics principles to construct two computational models on GlowScript, one that only accounted for gravity and one that accounted for both gravity and air resistance. Lastly, I compared all three of the models on the same graph to analyze the data further. This video that is uploaded to Tracker shows the trajectory of the object moving in a projectile motion. The red dots highlight the center of mass of the object as it moves in each time frame. The surroundings of the system, such as the air resistance and gravity, all play a role in this observed motion. From the data collected from Tracker, I was able to find the initial position of the ball and the initial velocity, and I plugged this information into the code in GlowScript. Along with this, I also logged the ball's mass in kilograms and the start time and delta t, which is the size of each time frame. Now, the first computational model accounted for just gravity and no drag force. Here, B is equal to 0, which means that when we're calculating the net force would equal the force of gravity because the drag force would no longer be in the equation. Here, I used Newton's second law to update the velocity and position of the ball, and here is where I adjusted the vectors to show the direction of the forces. After I ran the code, the trajectory of the object was shown in the graph and in the animated model. Now for the second computational model, this one accounted for both gravity and drag. Here we see that B is not equal to 0, which shows that the drag force plays a role in affecting the motion of the ball. The code is the same as the previous computational model shown. The only difference is the proportionality constant for the drag force. This graph shown compares the trajectory of the object from three different models: the experimental data, the trajectory of the object predicted by the computational model with only gravity, and then the computational model with gravity and drag. We can see that the object that was affected by gravity and drag was closer to the trajectory of the experimental data, which was what we observed in real life. It makes sense that the computational model with only gravity is not as similar to the experimental data because when the ball was thrown, there were drag forces like air resistance acting on it, not just gravity. Some possible errors that may have caused these discrepancies include incorrect positioning of the center of mass of the object in Tracker, outside forces such as wind blowing, and rounding errors in the calculations. Now for some further analysis, do any of your models predict a terminal velocity? No. The models do not predict a terminal velocity because velocity is constantly changing in the y direction for both models, and the slope of the graphs do not end up at 0. Terminal velocity is present only when the force of gravity is equal to drag or when the net force equals 0. A similar experiment that I could design to find the terminal velocity of the object is to throw the object further and from a greater height to allow the drag force and gravitational force to balance out. For the next question, if the object was initially thrown straight up with the same initial speed as in the experiment, the time this object takes to reach the ground would be longer. The drag forces added to the net force and the increased y values would increase v hat, which would increase the drag force and thus take longer to reach the ground. Drag force opposes motion in both directions up and down and prolongs the total flight time. This was my lab report, and thanks for watching.